In the previous video, we talked about the situation where the intersection of the two members are non-empty. Now we modify the problem and say we want to ask that the intersections have the same size. Right. So for a set family F, let's ask any pair of them have intersection of size exactly k, and how large can F be? Okay, so that's the question, and this was actually proved in 1940, and Fisher proved that such a set family cannot be too large. And in his case, he worked on the uniform set family, so uniform set system. So, and for him, there was an application to statistics. So this was he devised this problem for the application in the balanced incomplete block design. I mean, actually, this is the balanced incomplete block design. Anyway, I will show you the more general version. So sometimes this is called the Fisher inequality because of that. But Fisher's version is uniform version, so here we don't say uniform, non-uniform Fisher inequality. So let's say k is constant, all right, and F be a set family let me say family of subsets of 1 up to n. If x intersection y is exactly has k element for all distinct xy in F, then size of this is at most something. Now let's try to guess what's going to be the best possible, right? How large can we make it? So one example, like when k is 1, right? So then I pick 1 union I and then just 1, right? This is gonna be n of them. That's okay. Well, it's true, but maybe you may not be happy. This is a trivial example. Anyway, when k is 1, you have an example. And indeed, that's the best possible. So the maximum size of a set family is at most n. And the proof is by using the rank inequality. So remember, in the first video, we talked about odd rule theorem, and this is similar. Okay. So let's say the m be the number of members of set family. Oops. Okay, so let's just say A1 to simplify. If AI has size k, then this is actually a trivial case. Then AI is a subset of AJ for all J, right? So assume I is 1, why not? by symmetry, we can assume that, then A2 minus A1, A3 minus A1, AM minus A1 is a partition of the whole set minus AI, right? Because they don't have intersection. Oh no, it's not exactly partition. Partition of the union. All right, so let me say this way. Right? And this is subset of 1 up to n minus A1. All right? So therefore, and each of them is non-empty. Therefore, number of them is 1 plus n minus A1. And A1 is size k, so it's 1 plus n minus k, which is less than or equal to n. All right, so if one of the set have size exactly k, then we are done. So from now on, we can assume that everyone has more than k element. We may assume AI has at least k plus 1 or I. All right. Now we're gonna construct a matrix. Right. So the rows are indexed by 1 up to n, and columns are indexed by 1 up to m. So mij is 1 or 0 if the I is in AJ, and otherwise it's 0. All right. Now, again, we do the same techniques. Let's say A to be M transpose times M, so which is like you have a 1 up to M here. So these are indexing A1 up to AM, and then 1 up to N, and here you have a 1 up to N, and here you have a 1 up to M. So when you multiply these two matrices, the column of here, the M is multiplied with the column of M, right? Which is row of M transpose. So what's gonna be this? And it turns out that Mij will be, no, not Mij. On the diagonal, you're gonna have, and what's gonna be the diagonal? The diagonal is exactly the size of intersections, right? No. No. These are the diagonal is actually the cardinality. Right? So diagonal is size of A1, size of A2, size of AM. That's the diagonal, right? And for all others, you have the intersection of AI and AJ, right? Because when you have a 0, 0, 1, 1, 1, 1, 1, 0, right? When you multiply these things together with that, the number of common 1 is exactly equal to the size of intersections. And the intersection is exactly k, right? So everybody here is k, everybody here is k. So let's write it as kj plus c, where j is all one matrix, all one m by m matrix, and C is a diagonal matrix. And the diagonal entries are non-zero. Whose, right? So positive. Right? All right, so that's the situation. So what can we do from here? Now we're gonna observe the rank of A is equal to rank, less than or equal to rank of M, because A is equal to M transpose times M. So rank of product of two matrices is less than or equal to rank of one matrix, and this is less than or equal to the number of rows, which is n. All right. Now we claim that A is non-singular. Why is that? Right, maybe this is probably an exercise on linear algebra, right? There could be many ways to prove that A is non-singular. I will show you one method. So here's an observation. A square matrix A is positive semi-definite if X transpose AX is non-negative for all X in Rn, Rm, right? Let's say this is M by M matrix. And then it is positive definite if in addition X transpose AX 0 if and only if X is 0, right? So equality holds if and only if X is 0 vector. And here's the thing. All positive definite matrices have the full rank. Why? Because if not, right, then there is a non-trivial y such that AY is 0, so that implies that Y transpose A YA 0, right? So this is easy proof. Why do I talk about that? Now let's see. So here's a claim. X transpose A. Okay, we have the KJ. KJ plus C is positive definite. Right? Let's see. Suppose this is 0. What does that mean? That means X transpose KJX plus X transpose CX is 0. Right? What is that? And this is nothing but the it's all one matrix, so X transpose and then all one, so it's a sum of xi's, right? Squared, right? Is it clear? Let me maybe maybe I can say the following. So this is actually J, right? And then you can look at this part, that's actually sum of the coordinate. So sum of the coordinate squared plus X transpose CX. That's gonna be like sum of the CI XI squared. But it's a k times square of something plus, I mean, just sum of the squares. So this is 0, that means as these xi's are real, so that means xi's are real for all x. So x is 0. So that means kj plus c is positive definite. So this implies that kj plus c is non-singular. So rank of kj plus c is equal to m. So m is less than or equal to n. All right. Okay. Now we're going to talk about the application of Fisher's inequality. Here's an application in the geometry. So suppose there are n points on the plane such that not all of them are on one line. Okay, then there are at least n distinct, okay, so initially these are distinct points, n distinct lines through at least 2 of the endpoints. So what's the problem? So for instance, I have these 3 points, then I have I have 3 lines. I might have 4 points. In this case, I have many lines, right? What's going on? But if in some situations I only have right, small number of lines. In this case, I have 1, 2, 3, 4 lines. Right here, you have 6 lines. 4 choose 2. And the question is, can you have a configuration which has small number of lines going through 2 points? And the answer is, no matter how you try to make it, you will create at least n lines unless all of the points are on the one line. In this case, you have only one line. All right. So that's the problem. And here's the proof. Okay. Now, so let S be the set of lines through at least 2 of the endpoints, right? And for a point x, let AX be the set of all lines through x. Right. Now you have a family. So let's look at the AX intersection AY. The number of lines going through x and y is exactly 1. Right? So you have a set system, right? So AX1, AX2, AXM. So if you start with the m points, you have m of these sets where pairwise intersection has exactly 1 element. Right? Pairwise intersection is exactly 1 line. So by the non-uniform Fisher's inequality, oh, I should also say that these are distinct. Oh yeah, yeah. Since not all of them are in one line, ax is at least 2 for all x, right? So this implies that ax is not equal to ay because their intersection has size 1. So this means number of sets is at most, number of points. Okay, number of points is at most number of ground set, right? So ax is subset of S, and S is number of lines, right? So the number of lines is at least n. That's the proof. All right. Actually, maybe it may be interesting to see another proof by using algebraic method. So here's an alternative proof. Maybe essentially it's the same, but right. So let P1, P2, Pn be the point, and L1, L2, Lm be the lines. And suppose that number of lines is less than number of points. Then what we do is we construct polynomials. So Qx be the sum of all these polynomials, where inside you have this xj when pj is on the KAIST line. So x is in Rn. Now, this is a sum of the squares of linear polynomials. And since the Qx is 0 if and only if all these sums are 0, and number of terms that we are adding is m. So because you have only m equations and you have n variables, by the linear algebra, right, since m is less than n, there exists a non-zero x star, right? So x1 star dot 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 xn star, such that qx star is 0, right? But now let's expand it. So qx is, what's gonna happen for any 2 points, right? It's the sum of, I'm gonna expand the square. So for 2 points on the line, there will be xi times xj. But there's only one line going through 2 points, so it's gonna be like for all ij less than j, you're gonna have xi xj, right? And then for each square, right? So xi square will occur like exactly the number of lines times, right? So this from I1 up to n, xi square occurs maybe alpha I times, where alpha I is the number of lines through pi. All right. Yes. And alpha I is at least 2, because not all of them are on one line. So I'm replacing it by 2. So this is a sum of xi squared plus sum of xi squared. And right? So that means qx star cannot be 0 because x star is not a 0 vector. So this is non-zero. Contradiction. Right? So that's another proof. I think essentially they are same proof, but it's a short proof. All right.